Okay, so good morning, everyone. It's a pleasure to have Shapiro here with us today. Shapiro is a professor at Juiz de Fora, and he completed his studies in Tomsk University in Russia. He also spent some time in Zaragoza as a postdoc, and he works with quantum gravity, QFT in curved spacetimes, and cosmology. So please, Shapiro, take it away.
Okay, thank you very much, Marcia, Alvaro, and Dmitry for inviting me. I'm very happy to come here again. So it's a very beautiful place and new building, which is luxury, but unfortunately there is no swimming pool anymore. so which was nice in the first version. So I will tell about, most of this talk will be the review of the problem of higher derivative quantum gravity and respective problem of ghosts. Ghosts are unphysical particles which are very harmful potentially, and I will show how people deal with them. And then at the end I will show our last paper about what I call confinement of ghosts, and my collaborator Gaston Crane doesn't like it. He said that it's not correct expression, but since I'm not QCD expert, for me it's the same thing more or less as forming bone states. So I will try to convince you that this is probably the unique possibility to have quantum gravity. So consistent quantum gravity. So this is the what I will try to tell. So I will discuss semi-classical approach and higher derivatives. This is important because in the last years there were some papers saying that in the semi-classical gravity, when gravity is not quantized, only matter fields are quantized, then you don't need to worry about higher derivatives and all problems are solved automatically. This is not true. I will show you this. And then we discuss briefly randomization in quantum gravity in general and start to discuss ghosts in renormalizables and super-renormalizable quantum gravity. And I will touch the possibility to have complex ghosts and restore unitarity of the S matrix. Then we see how it works with the ghost-induced instabilities in cosmology, which is most explored part, I would say. And then this part which I said about forming bone states of ghosts in super-normalizable version of quantum gravity. So this last part I think I will skip. This corresponds to this paper with Wagner, who was a colleague of Publio, who is now postdoc here in University of Saint-Jean-de-Rey, and then they both were my students. So I will basically discuss what we did with Philippe Salis, with Patrick Peter from Paris, and the last work with Assorey, Crane, Miguel Pardina, which was last year published. So very good. So if somebody is interested in the subject, I can refer to this textbook on quantum gravity, which we published a few years ago with my former supervisor, Buchbinder. I think it's first textbook on quantum gravity. There are exercises, so if you want to learn the subject, I think it's quite possible. Okay. Also, there are my lectures which were recorded in 2019 in ICTP Saifr in São Paulo. There are 5 two-hour lectures, and some people actually use them to learn the subject and ask me to answer questions, which is nice in principle, especially if these people go well after that. So also we recently published a huge collection of reviews, which is this handbook of quantum gravity. It is 6-volume edition, 4,400 pages. And this Cosimo Bambi and Leonardo Modesta asked me to help them in organization. So you can find basically reviews written by best experts in this edition on almost all parts of quantum gravity, including my reviews. I wrote one review about perturbative quantum gravity, which covers also this part of the subject of today. Good. So let's go. So first of all, let's start with relativity. So we know that relativity is a very successful theory. There are many tests, and if you take the book by Clifford Will, for example, you will see the big list of tests of relativity, and relativity gloriously passed all these tests. And part of this are verifications of Newton's law, because we remember that 33 years ago there were discussed possibilities that some, in string theory, some extra dimensions are not completely compactified, and at 0.1, 0.2 millimeters there will be deviations from Newton's law. And we know that this doesn't happen because one laboratory in Bloomington University in Indiana checked that Newton's law works until 10⁻⁵ millimeters. I was in this laboratory, they made for me excursion there. Then I understood that I was in an important place. So relativity is very successful in all respects as physical theory. But as any other physical theory, it has limit of applicability. And we can see these limits because in the most important solutions of relativity, like cosmological solution and black hole solutions, there are singularities. Typically, in black hole case, singularity is in the 0 radius point. And this means that if we approach this point, everything explodes. The matter becomes infinitely dense and curvature becomes infinite. The same in cosmology. If we go to the very early cosmology, then we find singularity. And this probably indicates that relativity has to be modified near the singularities at least. And this means that you can, of course, try to modify the action of relativity by hand, such that singularity gets avoided. But there are also possibilities that these deviations are because of the quantum effects. And some people like me like this idea much more, because this enables us to put some restrictions on the modified gravity, because if you don't put such restrictions, you have infinitely many ways to modify gravity. And this is not, especially because in this region close to singularity, the expansion in power series in curvatures is not going to be efficient. So it makes a lot of sense to put some constraints instead of dealing with infinite ambiguity. So dimensional analysis, which most of you probably know, goes as follows. So in the normal physical scheme of dimensions, there are three fundamental constants in the Gaussian system of dimensions: speed of light, Planck constant, and Newton constant. And you can solve this trivial system of linear equations and find the units of length, time, and mass, which can be uniquely constructed from these three fundamental constants. And we can see that this is a very small length, very short distance, 10⁻33 centimeters. Like, for instance, quantum electrodynamics works until the scale 10⁻12 centimeters. So you have 21 orders of magnitude, the difference. And time is 10⁻43 seconds, which is very short period of time. And mass is 10⁻5 grams, which is macroscopic, actually. Mass, very small, but still macroscopic. But if you transform this into units of particle physics, it's 1019 GeV, which is a lot, which means we are like 11 orders of magnitude above the scale of the ultra-high energy cosmic rays, and 15 orders of magnitude above the limits of accelerators like LHC. So, how you can interpret this? So we can look at this the following way. These are the scales when simultaneously you need relativistic, quantum, and gravitational effects. But this, of course, is not conclusive. And there are, if you take this handbook of quantum gravity, you will see that there are a lot of different approaches. Some of them, regardless, I was one of the organizers, but big fraction of these approaches I didn't hear about before we started to organize this edition. So there are people do a lot of things. But in principle, I have some personal classification of how you can do quantum gravity. So the first possibility is to quantize gravity as a field and quantize matter fields. This is most natural and most obvious way. Then there is another possibility. You can say, okay, gravity is different from other fields. Gravity is a geometry. Then we don't, for example, and then we, by definition, don't quantize gravity. We quantize only matter fields. This is called semi-classical approach. And the third possibility is, as I used to say, quantize something else. For example, in superstring theory, you don't quantize matter, you don't quantize gravity, you have to quantize some object which is called string, which lives in the artificial target space, and then all interactions, all fields are supposed to emerge effectively at low energies. This is, from 80s, is considered a very important approach, and it has a very rich mathematical and physical developments. So, but these two approaches look very different, but they have something in common. And this something in common is the presence of higher derivatives. In all three approaches, you have higher derivatives, and we have to solve the problem of higher derivatives. And all three approaches have different ways to solve a situation with higher derivatives. Let me explain this. So we start with semi-classical, this unique transparency about this. So why it is so important to have semi-classical gravity? Because you put together two things which are existing. About quantum gravity, we have no proof that quantum gravity is something real. Of course, in cosmological perturbations, for example, we know that to have initial spectrum of the cosmological perturbations, you need to quantize gravity. But in principle, this is not very convincing. Maybe you quantize gravity in some sense. It's still not a quantum field metric. But matter fields are for sure quantum. Okay, we have many proofs of this. And in generativity, since we have so many tests of generativity, we know that the concept of curved spacetime is correct. So it is something real. So if we put these two real things together, we get quantum field theory of matter fields from curved background. And then it turns out that if you want that this theory is consistent, you need to add to Einstein-Hilbert action with cosmological constant, you need this term with 4 derivatives. So it's very useful form of this action. It has square of the Weyl tensor, square of the scalar curvature, Gauss-Bonnet term, which is topological in 4 dimensions, and box R, which is surface term. So it's important to understand that without one of these 6 terms, the theory is not renormalizable. Okay, and in principle, if we don't put one of these terms into classical actions, this term will emerge in quantum corrections, and probably with infinite coefficient, and then you will have to add it anyway, or subtract it with artificial fine-tuning of randomization conditions. So in principle, in semi-classical theory, the situation is very close to quantum gravity, in the sense that these c-square and r-square terms appear. They are interesting because c-square is responsible for the spin 2 part of the action and of the propagation of gravitational mode, and r-square is responsible for scalar mode propagation. So actually, while r and lambda have both. So if you don't put c-square, for example, then theory has no ghosts, as we shall see. So because it's equivalent to a scalar field, and depending on sign, it may be free of unphysical states. But if we put c-square, and without c-square the theory is not renormalizable, then you have in the spin 2 sector, tensor sector, you have your ghost-like states. In quantum gravity, situation is similar. So we can prove that the divergences are covariant. Okay, and there are several proofs. The first proof was given by Stella in 4 derivative gravity in 1977, and the last proof was like about 2018 by us, but Professor Lavrov and me. a little bit more complete than Stella did in 77. But what we know is that if you have quantum gravity theory, the theory with diffeomorphism invariance, then at quantum level, all divergences in all loops are covariant. Okay, and then the form of divergences depends on the power counting, and power counting tells us that if D, capital D, is a superficial degree of divergence of pair loop diagrams is 0, it means that you look only to the logarithmic divergences. And D, small d, is the number of derivatives of quantum fields in the diagrams. Then you have this relation in Einstein gravity. What it means? It means that D is 2 plus 2p, p is number of loops. If p is equal to 1, you meet 4 derivative divergences of these 3 types, for example. If you go to the second loop, p equal to 2, then you have 6 derivative divergences. This was confirmed first time by Gorov and Sagnotti in this paper. And the last term is remarkable because even if we exclude matter, then these 3 terms on shell give you finite S matrix. But this not. This term violates this, and you have a real breaking of renormalizability. So at 3 loops, you are going to have 4 more terms and so on. So in principle, the theory is non-renormalizable, and it means if we just follow this standard quantum field theory logic, to calculate any quantity, you need, in all loops, you need infinite amount of counter terms. This means infinite amount of renormalization conditions, and correspondingly, you need infinite amount of experimental data. And in quantum gravity, it's tragic because actually we have no experimental data at all. And so infinity is much more than 0, so we are in a bad situation. So what we can do about this?
Just about the status of renormalizability, you show that there's only one way to achieve renormalizability. So what's the status really? Is it there are other theories like supersymmetric gravities, right? N equals to 8 that is claimed to be renormalizable.
Yeah, you know, when I was in my first conference in my life, it was '84, and there was Renate Kalar speaking, and somebody asked her she spoke about supersymmetry, supergravity. It was '84, and somebody asked her what is the perspective on quantum gravity, and she said, we will solve it in a couple of weeks. I'm waiting for the new information about n equal 8 supergravity, and we expect that beta functions will be 0. This means the problem is solved. But 41 years after, the problem still is not solved, and the reason is the following. Even if supersymmetric theory solves the problem of renormalizability, okay, like cosmological constant problem, okay, in supersymmetry you solve it, but what you need is the real world, and in the real world there is no supersymmetry, so it is broken. So if it is broken, it means that this, for example, R square terms, R mu square, R square, Ricci square, they will be generated at lower energies with logarithmic corrections. And so you will have those problems with phantasmas, with ghosts, which I will describe anyway. So in my opinion, it does not solve the problem.
So the statement is that, is there a theorem proving that it's the only way, or is it just the only known example? That's my question.
No, it is very general. It's very general. But if actually I'm not expert in supergravity, so if you want to go to this handbook of quantum gravity, there is a section of supergravity organized by Jim Gates, and so you can see there what Jim selected as review papers. Okay, and I think it should be very convincing, but it's not my area, so I cannot say much about that. So here we are, we see that actually quantum gravity based on Einstein theory is not working. So what we can do is to go in 2 ways. One is to change standard perturbative approach to something else. For example, use what people call functional normalization group, this is the way you can ignore the problem of renormalizability. This is very interesting approach, but it has some, I would say, overwhelming ambiguities. So it's very difficult to say that something can be really calculated in this approach, but it depends on your evaluation. Like in this handbook, we invited people and they made very nice section about this. So, and then we can change the theory. There are many other approaches you can see in the handbook. There are many, like effective quantum gravity, which is now very fashionable. I will mention it later. So we can also change the theory and take another theory to construct quantum gravity. And this is what I will describe. So the first possibility is this. We can add to the classical action these higher derivative terms with square of the Weyl tensor and R square. This is somehow very natural because we know that this term emerged anyway due to matter fields corrections. So then the power counting is completely different. You see capital D is as usual 0, and the number of derivatives in the diagram is at most 4 minus twice the number of vertices with 2 derivatives and minus 4 times number of vertices with cosmological constant with 0 derivatives. So it means that theory is renormalizable because it's covariant and it has at most 4 derivatives. Then there are possibility to have terms with 2 derivatives, which is R, and 0 derivatives, which is lambda. So in all loops, you have this formula. This formula does not depend on the loop order, and you have perfectly renormalizable quantum gravity. This was the paper by Stella in '77. Very good. So, unfortunately, you have to pay the bill, and the bill is heavy because you see the spin-2 propagator in this theory has this structure. So you can write the spin-2 propagator in this way, and here we see that there are 2 particles instead of 1 graviton, which is typical for relativity. There are 2 particles. One is graviton because the sign is positive; it means positive kinetic energy, and mass is 0. And the second particle is massive particle with negative sign, which is exactly the particle which people called massive unphysical ghost. And the role of ghost is very interesting. It was explored by many people, and historically it started with a work by Ostrogradsky in 1850. And he explored, of course, not quantum field theory, but he explored classical mechanics with 4 derivatives, and found that there are explosive solutions, there are instabilities. Then there was a paper by Weltman. I think it was his first paper in '63, long before, like 8 years before they made papers with Hooft, which gave him Nobel Prize after. And in this paper, he analyzed it. It's a very big paper, I read it, very difficult to read actually. He analyzed the scattering of very heavy massive particle with negative kinetic energy, that is ghost, with a lot of light normal particles. And he found the following, that the dominating cross-section is that this heavy particle accelerates and energy becomes greater and greater, but it remains negative, and it emits a lot of positive energy to the positive energy particles. Then there are review papers by Richard Woodard, like these 2, and everything is about Ostrogradsky instabilities. And in these papers, and we know that this is true, Richard discussed the following, that if you have ghost, then everybody can understand what will happen. You have negative kinetic energy particle. There is a principle of the least action. So this particle wants to do what? It wants to accelerate, because if it accelerates, the action becomes smaller, so it goes to the minimum of the action. If this particle is isolated, if this particle is free, then it cannot accelerate because the energy is conservative. But in gravity, nobody can be isolated. Any massive body, any object which has energy, even photon, is capable to emit gravitons. So this particle with negative kinetic energy, it is never isolated, so it will accelerate. And as far as it accelerates, it will emit gravitons. And when its speed approaches speed of light, it will have huge energy. It will accelerate even more and will emit more and more gravitons. And finally, in a very short period of time, remember that the mass is of Planck order of magnitude, we will have an infinite explosion of energy. Okay, maybe we don't get this particle by itself, but we will observe infinite outflow of gravitons. And we cannot live in this world. Please.
Excuse me, I just want to connect it with some knowledge that I recall from old times. Remember, people were speaking about ghosts in QCD, like Fadeev, Popov, and so on. But then my understanding was that you can get rid of them by choosing particular gauge. Here, can you do a similar thing?
No, because the only common thing is the word ghost. People used to call Fadeev Popov ghosts because they are bosons and have fermionic statistics. And it has nothing to do with this because they have positive energy. And moreover, they are not they are ghosts because they do not appear by definition in the external lines of the diagrams. Okay, these are completely different. This has nothing to do with gauge ghosts. It's not Fadeev Popov. It is real physical particle which is in the spectrum. Okay, it has nothing to do.
So in principle, you could observe it in the accelerator.
Not only in accelerator, we could observe it in this room, and we cannot finish the talk. I mean, it is going to be absolutely disastrous. Okay, but it doesn't happen. I will speak about that. Okay, so we see that existence of such a particle is very bad. So we cannot finish our talk, we cannot go for lunch, we cannot do anything. We are going to explode in a very, very incredibly small fraction of a second. So this doesn't happen. So we have to explain why it doesn't happen. So one of the people, of course, tried to solve this. And I will show different approaches. I classify them not in the historical sequence, but in the sequence of complexity. So one possibility was this. We tried with Manuel Sorey, Jose Luis Lopez, and me. We constructed supernormalizable quantum gravity. So you just put here polynomial action. You add some amount of boxes between the two R, C square and R. And then your power counting is very nice, it's this. So you see that if K number of this N, it should be N, oh my God, I always use the wrong version. So it should be N, capital N here. So if you have like N equals 3, so you have 10 derivative theory, then all divergences are one loop. Starting from two loops, you have no divergence, this very nice theory. And our initial intention was to have the situation when you have real spectrum and all particles are healthy and only the last particle is ghost, and this last particle may have infinitely large mass. And we thought that infinitely large mass may be not offensive. It doesn't work. It was proved in this paper that it doesn't work. Why? Because if you have real spectrum of masses and put these masses in the sequence of growing mass like here, then the signs alternate. What it means? It means that first particle A0 is positive because you have graviton, then the lightest massive particle is ghost, then you have normal particle, then ghost again, and so on. So you never ever get rid of ghosts in this way. Anyway, this theory is nice because it is super normalizable. You can even calculate exact beta functions. So if you have some method like functionalization group which pretends to give you exact beta functions, you can try to reproduce this result because this is really exact beta function. One loop is exact in this case. Very good. But as I said, it doesn't solve the problem of ghosts at all. So we have two sides of higher derivative theory. One is that if we do not put higher derivatives, they go back in the quantum corrections. If we put higher derivatives, then we have this massless graviton, massive spin 2 and massive spin 0 in principal particles which start to kill you, kill your world, better say. Okay, so there is some approach which many people consider standard. This was formulated by Simon in 1990, and then there was paper by Parkin and Simon, and then one more paper by Simon. The idea is the following. You have to make like you do in QED. In QED, you know that one-loop terms generate higher derivatives, but you treat them as small perturbations, otherwise you end up with the so-called runaway solutions. So why don't we do this here? We can say that all higher derivative terms by definition are small corrections, and they should be treated perturbatively. Then it changes the game completely, because it means that this structure of propagator, oh my God, this structure of propagator is impossible, because the propagator is by definition only 1 over k square. Okay, and it looks nice because it solves the problem. So it means that you put some definition which solves the problem. But here it is quite different from QED or any quantum field theory, because this action, as I explained, should be renormalized. It's not just perturbative finite correction. It's classical action which has to be renormalized. So if we introduce this as a kind of ad hoc procedure, we want it, so we do it. Another point is that we have a lot of ambiguity, like R-square term. R-square term, in the third paper, Simon required to forbid R-square term. But R-square term is behind the so-called Stravinsky inflation, which is the most simple and most successful until now model of inflation. So you have to introduce some system of definitions which forbid you to use very successful model. And moreover, R-square is free of ghosts. So you kill it for nothing, basically, which is not good. Then there are other ambiguities. So what you do with R cube, this term, and many others, you treat them as perturbations or not. For example, in Stravinsky inflation, it's difficult to treat R square at all scales as perturbation, because the coefficient of R square should be about 1 billion, half of billion, better say. Okay, so because of this large coefficient, scalar mode, massive scalar mode, is not tachyon, but it's not ghost either, but it's very heavy, but it's not of the Planck order of magnitude, it's much lighter. So you need some reason to treat it as perturbation. Now, here we have certain ambiguity, okay, at least. So, moreover, our initial purpose of quantum gravity is to deal with singularities. In near singularity, you have all scales, even such scales when all these terms cannot be treated as small perturbations. They are large, numerically large. So it's not a perfect solution, let's say, but I will show you that this logic of this Simon's paper has some success in, okay, but maybe in a different framework. Another comment I will give about string theory. People used to think that string theory is free from the problem of higher derivatives. Up to some extent, this is true, but only up to this extent. So how works string theory? I will give you on the example of the sigma model approach, which I know because other approaches I'm not familiar with. So you start with this sigma model action. Okay, here sigma is a two-dimensional integration, the surface which you have in a target space. The dimension can be 26 for bosonic string, 10 for superstring. And then you have alpha prime. Alpha prime is a parameter introduced, as far as I know, by Polyakov to stress that these two terms are classical and these two terms are quantum, as Fradkin and Zeitlin and Callan, Friedan, Martinez, Perry explained to everybody in '85. So you calculate a conformal anomaly in this theory, because classically this is conformal, but these two terms violate conformal symmetry. You calculate anomaly, and then you require that anomaly cancels, because you impose equations for G, A, B, and T, for so-called tachyon term. So this cancellation of anomaly in 2 dimensions provides you equation in D dimensions. And then, those are papers which changes the game completely in string theory, because 2 years before these papers appeared, I saw some other papers and asked my supervisor, I was a student, why don't we do it? We know how to make these calculations, what these people do. And he said, no, nobody will ever pay attention to this because it's no local, very strange no local theories. And after these 2 papers, things changed completely. We know that during decades, this was considered as, let's say, main line of development of science. But what it means, the main merit of Fradkin, Zeitlin, and paper was that at lower orders in alpha prime, you generate R in the d-dimensional effective action. So you generate, as I said, you quantize something else, you quantize string, and you generate R as low energy manifestation. And then you said, okay, I don't need generativity to postulate generativity, I just need to take this d-dimensional action, compactify extra dimensions, and I have my gravity. So everything works. However, if we go to the next order, to 2-loop, then you get your R-square corrections back. They come with alpha prime. It's very bad. So what people did about that? The solution was found by Barton-Zweibach in '85. And then there were papers by Desirelli, Zetlin, and so on. You do this reparameterization. Why it is possible? Because G mu, Gij, is not a quantum field. It is external field. It's a set of parameters, you want to say. So we can make this reparameterization and remove these ghosts from here. So these three terms must form Gauss-Bonnet invariant. The next order also must form something like Gauss-Bonnet invariant, and so on and so forth. And your propagator is free of ghosts. So this approach works. These people analyzed it in details. It works very well, but there are some questions. And the first question was that we noticed this with Antonio Maroto from Madrid in '97, that actually, if you do not fine-tune X2 and you just make Gauss-Bonnet plus R-square, okay, then plus this R-square, then you killed all ghosts, but you have your R-square. And R-square is good. R-square is something you need for Stravinsky inflation, for instance. So, in this case, you have an ambiguity. You can kill R-square or not to kill R-square. At that time, when I started to understand this, I went to some string people and asked them, what is your policy? What you kill and what you don't kill? And the answer was, we kill everything we can kill. Which is a reasonable politics, but not in all possible situations. But there is one subtlety even in this, if you accept this ambiguity. Look at these formulas again. So this fine-tuning, which you take with this Zweibach transformation, must be absolutely precise. If you make a huge mistake in the coefficient x1, it means that square of the Ricci tensor comes back with a huge coefficient because your mistake was small. It's kind of seesaw mechanism. So you make a very small mistake, like 10 minus 10, and your ghost comes back, but with a 10 orders greater mass. It means that you immediately have destruction of the world. But it's very difficult to control this. Why? Because we know that at low energies, the real world is not string theory. The real world is QED and other field theories. So you have to impose the following restriction, that all physics, absolutely all physics, must be controlled by string theory. You cannot go out of the string theory even for a millisecond. If you do this, you get your R menu square with a huge with some coefficient, with small, okay, but this gives you ghost and you explode. So theoretically, this is not very satisfactory, let's say. So you need infinitely many precision or fine-tuning for infinitely many parameters, because this is just the first term. There are infinitely many other terms, and all of them must be infinitely fine-tuned, okay, to get rid of ghosts. In this sense, and only in this sense, string theory resolves the problem of higher derivatives. Okay, so one can choose, like it or not. There is another view of this. There was a very nice paper by Gross and Sloan, and it's a complicated paper about basically other subject, but they made the following observation. They said, okay, look, if we don't need Zweibach transformation, if we restrict our interests to the terms, to the energies which are below the Planck scale, then why would we care about these R-square terms? They may appear, but they were harmless, because we are at small energies. It's very nice. It goes according to what we call effective field theory. So you can see this paper of Donahue. This is not my subject today, about effective field theory by Donahue, by Cliff Burgess. And there is a section, they organize it for our handbook, and you can learn what these people do in effective quantum gravity. Okay, it's not my subject today. I have certain divergences with Donahue, but anyway, it's very nice approach. But this approach means the following: you just give up from high energy quantum gravity. You say, okay, I want quantum gravity only as low energy theory. So the initial point with the singularities is out of my scope, let's say, beyond my scope. Very good. So another possibility was noted by Zeitlin in 95, 10 years after they invented with Fradkin this way of getting conjunctivity from string theory. So instead of making Zweibach transformation to fit everything to Gauss-Bonnet, you can do the following. You can fit to this particular construction. Einstein tensor, this non-local term, and R menu with exponential dependence on box. This is interesting because in this theory, you can prove that there are no ghosts at tree level. So the theory is free of ghosts. And actually, it turned out many years after that it is a renormalizable theory. Okay? So people, interesting that this result by Zeitlin was rediscovered many times, and the last PRL paper with the same result was published 16 years after, which is nice. These things happen. so it was rediscovered at least 3 times. So, very good. So, so people started to think, even before Zeitlin, that non-local models can be very useful to construct good quantum field theory. So first was paper by Krasnikov from Dubna, and he just made general analysis about non-localities, and then Tombolis made this proposal of non-local gravity, and then Modeste and Rachel made series of papers, many other authors, so it is just, imagine it was a section for the handbook, so it was like very serious. So the people start with this theory, which is super normalizable. I proved this in this paper. And they, at tree level, there is no ghost. This means in particular that the, by assumption, the Coleman-Lehman representation shows consistency, okay? However, you can show, this is my paper because some people criticized us previous papers and I had to respond. So counting ghosts in the ghost-free theories. So what I show is that this theory is free of ghosts only at the tree level. But if you add your loop corrections, even if you make this theory finite, because Modesto and Rachel, they found finite quantum gravity without any divergences, still at quantum level you have infinitely many complex ghosts, ghost-like states, better said. Okay? How it works? It's very simple. Look, you have this kind of equation at the tree level, p squared multiplied by exponential of alpha p squared equal to 0. Of course, exponential never equals to 0. Very good. But if you add quantum corrections, then instead of exponential, you have something like exponential plus log, or exponential plus polynomial, if you don't have divergences. And this has many solutions. It has infinitely many complex solutions. So it's something very simple, what I said in this paper. So we have situation when we can modify our theory in different ways. You can have polynomial theory, as we suggest in 95. We can have this exponential theory as 97, okay, and so on. But ghosts never disappear completely. So what people historically did it? Historically, it started with a paper by Tombolis, and then Salam and Stredi, and Antoniadis Tombolis, and there are many papers of this type. And the idea was that if you start with a theory which has ghost, massive ghost, add loop corrections, then your ghost splits into 2 complex points. And then, like in QCD, these 2 complex states disappear asymptotically. Like Leonardo Modeste, he likes a lot this Lewick quantization, and I will show next transparency, it's automatic. So people worked a lot on this, and then there was a nice paper by Johnson, very short paper, and he proved the following, that all considerations in Salam and Stredi did very general, but Tombolis were based on some assumptions about quantum corrections, and Johnson proved that those assumptions don't work. You need Dressed propagator of gravitational mode in all loops to make a conclusion, and we don't have this. So another approach was published by Stephen Hawking. The paper was "Who is Afraid of Higher Derivative Ghosts?" Very nice name, and he basically said something very clever. He said that ghost is not an independent particle. It always appears together with graviton. So you need to construct a field theory which takes this into account. I was very excited. I went to some very good people and asked their opinion, and the best formulation was the following. I will not tell you who said that. This is the opinion of a non-expert, so we cannot take it serious. This is up to some extent is true because we don't know how to make a theory of two fields together. Okay, I will show you something in this direction later on, but in principle it's not easy to imagine, especially because ghost is a massive particle and it moves very fast, very slow, and graviton is massless particle, so it moves with the speed of light. So how they can merge together? It's difficult, right? However, we can do something different. We can start with the sixth derivative gravity instead of fourth derivative gravity. In sixth derivative gravity, there are two particles. One is ghost, and another heavier one is a normal massive particle. The original idea of Modesta and me was the following. Let us imagine situations that these two particles go together, and the difference between the minus energy of interaction gives you the energy of the composite particle. But we ended up working on complex case of complex poles. So you have this P2 and P0 are for second order polynomials, or first order polynomials, sorry. So you have some conditions which give you complex conjugate solutions. There are no ghosts, no tachyons, there is some combination of them. And finally, you can prove using optical theorem that in this theory, using Levy quantization, which is very important, your S matrix is unitary. S matrix is unitary looks nice, but it is not completely solves the problem, especially using Levy quantization. Why? What is Levy quantization? Qualitatively, something simple. You have complex poles, and you assume that your system is isolated. Then you see that the particles have no energy to develop to infinity, okay, because system is isolated. However, let us remember that we are in gravity, and in gravity nobody is isolated. So in gravity, Levy quantization is not going to give you a definite solution of the problem, unfortunately. So, so we can think even more. Do we need to think too much about unitarity of S matrix for gravitational modes? My opinion is that no, because unitarity means that you have in states and out states, and they are free particles. But in gravitational world, nobody is free. So maybe S matrix approach is not safe in this case. So what is safe? What is the criterion? And the criterion is stability. So we need something more simple than classical, than quantum unitarity. We need to check that our theory is stable with respect to classical perturbation. And the result is well known. It was Stravinsky in '83 studied this theory even with quantum corrections owing to anomaly, and saw that there are no growing modes. So then we did the same with Giulio Fabriciano Pilinson, that Hawking, Hertog, and Real did something similar, we did and so on, and nobody ever saw growing modes in this theory. And at some point with Felipe Saris, we asked why. And the answer we found was the following, that if you don't put initial seed of cosmological perturbations of the Planck order of magnitude, there are no growing modes. The plot is like this, so the modes are disappearing in the expanding universe. But if you put your initial seeds of half, this is k is in Planck units, half of the Planck mass, then you have an explosion. So it means that this Simon's idea about treating higher derivative terms as perturbation works very well. But for this, you need to put restrictions on the initial conditions. You need some physical law which forbids gravitons to accumulate with a very high density. Basically, it means the following. You have Minkowski space. You have Minkowski space, and you have ghosts in the spectrum. you won't generate ghost from the from nothing, from flat space in Minkowski. What it means that the Compton length of the ghost will be of Planck. Okay, it's 10 minus 33 centimeters in cube. So you need to concentrate gravitons, okay, to compensate, to fit with energy conservation, with a huge density of gravitons in this place, to take one graviton from the Minkowski. And there should be some rule which forbids you in physics to take this graviton from Minkowski, because otherwise we should not be here, right? so there is some hidden law of nature which forbids concentration of gravitons with the Planck order of density. Okay? Even we can require less than this. So this is the equation, typical equation for the gravitational perturbations, and you can see that these how to say, space derivatives, the gradients, always are divided by a square, and a is the conformal factor of the metric. So what it means? It means that if we consider initial seeds of perturbations of the Planck order, but universe is expanding, this was done with Patrick Peter, what happens is the following. The plot is like this. If we go in this plot to the beginning, we see that the first stage, yes, there is an explosion. But then if the expansion of the universe is fast, this explosion disappears. So actually, you need to insist that you can concentrate gravitons. You can concentrate gravitons with the Planck density only if the background has very strong gravitational field, and then there is no danger. Okay, but if you don't do this, we still don't have stability in our world. We can explode. Okay, an interesting test was done by Alexey Alexandrovich Starobensky with my former student Flavia Sobreira. She is now teaching in Campinas, and her student Anna Romero. We did the following. We took this theory. This is the simplest possible gravitational theory which has ghosts. We put R box R. This is scalar ghost, not tensor ghost. And we follow Simon's prescription and try to see what are the perturbations of this theory in the case of inflation. And curiously, absolutely the same work was done by Leo Medeiros, who is somewhere here, and his collaborators from Minas Gerais. And what is most funny is that results are the same. But they did not use Simon's approach, and we use Simon's approach. Why we have the same results? Because we did not go to the Planck scale of frequencies. If you don't go to the Planck scale of frequencies, you really have the same. Doesn't matter. These ghosts don't appear. They are not created from the background. Okay. So actually, we are protected until we don't go to the Planck densities. Good. But, so general situation is this. I have a very short time, right? So we need higher derivatives to have consistent theory, but at the same time, we don't have reasonable explanation why these ghosts don't destroy us. Regardless, we understand that they destroy us only if we manage to concentrate gravitons with absolutely incredible density. So how we can solve it in the fundamental level? And actually, in QCD, people know how to do this. This was a paper by Noboru Nakanishi in '75, and he found the following, that in QCD, in the non-perturbative QCD, at some point you have, for gluons, you have complex poles instead of real poles. And then these complex poles indicate that you need to form a bond state. And this is what Tambolis, Salomon Strady, Antoniadis, Tambolis, and so on actually always insisted, that they were interested in the complex poles. So recently this idea became very popular. This was first paper by Bob Holdam, and then Frasco with somebody. This was very complete paper by Modesto and Kalgani. And finally, De Brito was, and so on. I will show you what we did in the last paper with Manuela Sorey, Gaston Crane, who actually commanded this project, Miguel Pardino, which is a student of Asore. So first we took a very simple toy model with 6 derivatives with complex poles. Then we could write it as with auxiliary fields as the ghost sector, as normal 2 derivative fields with 2 fields, phi1, phi2, with some interaction which we put by hand. This is the biggest problem for a while. And then we started to see how we form a bound state. So we took this composite field and wrote its propagator in this way. Okay, we derive this propagator in the most simple possible way. Just take this diagram and transform it into non-perturbative by this trick, summing the, assuming that we can sum the perturbative series for strong G. And then we get the propagator for the bound state. And this propagator must have a correct pole and the correct residue. And it turns out that this is the plot which we have, and the, okay, I will go back for a second. So we see that this is, here is no, okay. So this is something we need. So we need that this line cross the 0 axis and with a negative derivative, which is exactly the case. So it means that we have a bound state out of ghosts. So what it means, imagine we go backward in time, we come to the Planck scale, and then we have 6 derivative gravity in the best case scenario when everything works for gravity. And then we have massive complex pairs of ghosts. But they are not ghosts, they form a bound state. And this bound state, after it evolves to a positive time, just as a composite particle. It works, okay? And so we have this, okay, so there was a change of order. so we finally have a residue which is positive and everything works well, but with certain restrictions for the coupling constant, okay? But it's important that we could construct at least model which makes the job. Of course, this model is very, very far from real gravity, okay? But still, we have this model. We can ask the following. Okay, imagine that we, remember that in QCD, which is simpler theory than this one, there is no analytic explanation of confinement after like 50 years of heavy work of many very clever people. So we cannot expect that this way of dealing with ghost problem will give us some definite answer in the next 50 years, probably not. But we can at least see that there is no other way we can explain. The problem is not to construct some gravity which we like. The problem is to explain why we don't explode. And this is probably the unique way to explain this, as far as I can see. So imagine this is solved. What we can say about the result? First of all, there are people like Guy Dvali and his collaborators which work on the theory where, from some reason, there is a restriction of the density of gravitons. In this theory, there is automatic restriction of Planck order of magnitude, some cutoff, and if the energy goes beyond this threshold, you don't have ghosts, you cannot accumulate gravitons. So in principle, the idea is in the air, I would say, and for many years. Then the first solution of the first output is that there were some works about trans-Planckian physics in gravity. The first paper was in cosmology by Jerome Martin and Brandenberger, and then there was some discussion about this. This paper by Garay and other people, they did the same with the black holes. And so it's quite complicated, but actually the result is, as I understood, not very satisfactory, because these people even did not like to contribute to the handbook. And they refused to contribute in a bad way. They said that we don't like to remember this. So, yeah, which means they have problems. If this story about composite of ghosts works, then they don't need to remember this, because it means that we cannot go to the trans-Planckian energies by definition. Now, then you have the natural idea to use these bound states of ghosts as a dark matter. And this unfortunately doesn't work because we made this numerical estimate of the density of bound states of the end of inflation. At the end of inflation is this 78 orders of magnitude compared to the critical, below the critical density, so it's negligible. We found after that, after inflation to nowadays, this bond states density compensate like 25, 30 orders of magnitude. Still there is 50. So bond states, if they are around, they are not very often you can find one. Okay, not very often you can find one. Probably it does not show up. Okay, so this is good news perhaps because these are exactly the particles which is difficult to find in the laboratory as dark matter particles. And finally, my time is over, so I go to conclusions. So we see that if we want to have quantum gravity which is not restricted to infrared, that's not effective quantum gravity, so we cannot do it without higher derivative terms. Then if we have the ghost in the spectrum, then the theory may be classically stable if the Planck order cutoff is imposed on perturbations. So if your gravitons cannot go beyond the Planck scale, then probably we are safe. And in principle, in theory, with 6 or more derivatives and complex ghosts, it's possible to have a confinement in the sense of forming bond states and not having offensive ghosts. And finally, the conclusion is that we have no definite solution to the problem of ghosts, but it looks like the solution can be found only on the way of confinement and in the QCD style. Thank you very much.
Okay, thanks, Shapiro. Let's open for questions.
Hi, Shapiro. Thanks for the talk. So one question that's confusing me is I'm not from this field. So when you have 5 or dimension 6 or whatever 7 higher derivatives, how can you make it renormalizable if you have a cutoff in the end? So I did not get it. How can you make the theory renormalizable if you have higher derivatives? So what's the trick?
The trick is that you just need to calculate the, okay, in simple terms, the number of derivatives in the vertices and in the propagator is always equal. But they enter the power counting in a different way. I can write you formula, I remember, okay? Mm-hmm. And it turns out that as more derivatives you have, better is your power counting. Okay, so starting from 10 derivatives in this case, you have only 1 loop divergences. In the infinite derivative series, like the exponential of box, only 1 loop.
I see.
As I did in this counting ghosts in the ghost-free series, I proved this.
Okay.
Because yeah, and in the non-local series, it's completely non-trivial because the power counting formula gives you infinite minus infinite. But then you go to the so-called topological relation, which is number of internal lines minus number of vertices. Both are infinite, but the infinity is the same. So, and you see that they cancel and you get only 1 loop divergences. Okay. Actually, many years, people asked me how to calculate for this non-local series power counting, and I said it's impossible because it's infinite minus infinite. And then once I started to explain to the guy on the blackboard why it's impossible, then I understood that I know how to do it because this topological relation gives you a result. So, and this created the confusion. So,
More questions?
I didn't understand. So in the end, do you have unitarity in your theory or not?
Well, it's a complicated question, you know. Unitarity, you can have, by unitarity, people understand 2 different things. Unitary S matrix, yes, if you have complex ghosts, you have it automatically in this theory. Okay, it doesn't matter, without confinement. But it's not physical unitarity in the sense that Cullen-Lehman representation is not well defined in this theory. Okay, there was, we wrote a paper about this, we started to write it 8 years ago and did not finish, and then we discovered that Modesta and Kalgani already published it. So, but anyway, it's now public. So you can have your theory, even non-local theory, and this Cullen-Lehman shows you that you have ghosts, basically, if you have higher derivatives. Okay, but they say in the paper that this is irrelevant, which I don't understand well. So because this is representation which picks up all spectrum, physical spectrum of the theory. So basically, you have unitarity of S matrix. It means that in the in state and out state you have the same particles, but these particles are ghosts, maybe ghosts. So this is not the unitarity you like to have. You explode and you say, okay, it's formally correct, which is not what you want. Okay? I answered to
Usually you just restrict the initial state not to have ghosts, and unitarity means that you don't produce ghosts in the physical process.
No, because unitarity in the traditional way means the following, that if you take Stella paper 77, first paper, he explains very well that you have in states without ghosts, because you don't admit that your spectrum, physical spectrum, real particles are ghosts. Then they enter this is S matrix approach, they enter the region when there is interaction. And when they go out, you have ghosts. So your theory is non-unitary, certo? So, but you need some mechanism which prevents this. And the mechanism is the following. If you have this forming bone state, then instead of ghosts, you have bone states on the right, on the out, which means you have everything is fixed, okay? But we don't have, let's say, mechanism explaining this completely. We have only a small toy model.
So very naive question. So you have negative energy states, which are ghosts, which are forming bound states. So their interaction energy is positive. It's like they repelling each other, actually. No. You have so your bound state should have positive energy.
You don't have in this model. You don't have ghosts. You have complex conjugate states. It's more complicated. It's like in Nakanishi and other approaches. So this Nakanishi paper is very popular. There are many others. So you have complex states, and they are not complex because you cannot have complex particle in this matrix, right? They form bond state. This is basically the game. But my original idea was the following. You won't have a real spectrum, one heavy normal particle, okay? One lighter, it's always true, ghost, and they interact very strongly. They interact, and then the mass of, it's very nice show. Mass of the bone state would be mass of the normal particle, okay, minus mass of the ghost, okay, and minus energy of interaction divided by c square, right? And then I said, okay, we can find, because in this theory we have interaction of the way you like. And then it still remains something for this mass to be positive. Okay? But it does not work. What Gaston Crane found is that in this way it doesn't work. Okay?
Okay, more questions? Okay, if not, let's thank Shapiro again.